here to introduce our TransitLabel system as a crowd sensing system for automatic labeling of transit station semantics, which is a joint work between Osaka University, Japan, and Egypt. Railway stations in highly populous countries have vast indoor spaces, and they are being visited by millions of people every day. For example, Osaka Station City in Japan has an indoor space of 20,000 square meters, and it's being visited by 2 million passengers every day. Therefore, many stations indoor location-based services like indoor navigation or point of interest finder and indoor analytics and etc. application have started to emerge. These applications need digital semantic indoor floor plan, like the one shown in the figure, which is a typical station indoor floor plan in Japan, where different stations semantic file, fare collection gates, platforms, and waiting line, and ticket vending machines and restroom are highlighted in the floor plan. Therefore, recently many commercial indoor map services have been launched by different companies and startups to try to build this indoor floor plan. However, these services are done manually by dedicated people, and they also allow buildings owners around the world to upload their map. This manual process is very tedious and takes enormous cost and time, so this impedes the scalability of this system, with Google Indoor Maps currently cover less than thousands of buildings worldwide. So the big question is it possible to automate the floor plan construction process? The answer is yes. Already there exist many crowdsourcing approach for automatic floor plan construction techniques, including one of our previous work. This system exploits user motion projectors inside the building to provide only the building general layout and identify rooms and corridor shapes and location. However, none of this previous system, including our previous work, provide names or functions of the semantics, which are the key requirement of any indoor location-based services. So all the previous work just only provides the building layout and the location of doors and the corridors without any semantics. To tackle this problem, we present our work, which is a crowd sensing system for automatic construction of semantic indoor floor plans for railway stations. The input of our system is actually unlabeled floor plan, which is generated automatically by our previous system, and it can be the input from any other similar system, and a set of passenger daily communication traces, and the output is a semantic floor plan like the one shown before. Our basic idea is that we observed that passengers' activities in railway stations have unique signature on one or more phone sensors. We leverage this fact to recognize passengers' activities in the station, and at the same time, as shown here, we track the user position in the station starting from the station entrance. After recognizing the event, the activities, we can identify their location, which is actually the user location at the activity time. Then we cluster all adjacent activity location samples by running DB scan on all discovered activity samples. And then we can estimate the activity location as the center of mass of all samples inside the clusters. Finally, we have the location of each activity, which is a semantic, because each activity is actually is connected by a semantic or uniquely associated with a semantic. For example, activity like buying a ticket is associated with ticket vending machine. Activity like drinking is associated with drink vending machine, and so on. So to achieve this, we have faced many challenges, like semantic signature is based usually on the user and the passenger behavior, which are prone to artifacts. Second, we have to conserve phone energy, and third, the indoor location estimation of the user has a lot of challenges, but we depend on the idea of previous work, which is called Unlock, which is published in MobiSys 4 years ago. In this system, we use the activity location as a landmarks to reset the dead reckoning error, and at the same time, after resetting the dead reckoning error, we will have a good estimate of the user location, and at the same time, because we get the activity location from the user location, this will have impact on the activity location and semantic location. And finally, we should preserve the user privacy. So we addressed all these challenges, and we provide our system for railway stations semantic classification. We basically depend on the user behavior while using this semantic to identify them. We broadly classify station semantics into two major main classes. The first class is the elevation change semantic, which include elevators and stairs and escalator. And the second class is other station-specific semantics like ticket vending machines and drink vending machine, lockers, fare collection gates and the platform, waiting lines, waiting rooms, and restaurants. We will identify all of this semantics. So we first need to know how to separate these major classes. We actually depend on the barometer reading because the first class, which is the elevation and change semantics, when the user is using one of these semantics, as shown on this green figure, there will be a significant change in the barometer reading, which reflects that the user is changing his level or height. On the other hand, when the user is using other class of semantic, which is ticket vending machine or other semantics, there is no change or little change on the barometer reading, which represents that the user is in the same level. We will not able to discuss now all of this semantic. We will get insight about how to identify some of them. We will first want to classify the station-specific semantics, and we will first start by how to identify coin-operated machines, which include drink vending machines and the ticket vending machines and the coin-operated locker. First, all semantics have a unique user behavior when he starts to use this semantic. For all coin-operated machines, the user has to walk to the machine, which translated into high acceleration variance to reach the machine. And when the user is using the machine, the user has to be stationary, so there is low acceleration variance. At the same time, there is a distortion on the magnetic field as shown on the gray curve. This distortion is by the metals and the electronic chip installed in this these machines. This distortion forms a clear peak on the magnetic field as shown in this figure, which can be easily detected by a peak detector. Finally, when the user finishes the interaction with the machine, he has to walk away. As all of these machines are usually mounted to a wall, so there will be the user has to change his direction, and this will be reflected into a very surge in a big surge in the gyrometer reading, as shown on the green curve on the. So this multi-sensor pattern we will use to identify. We have used to identify the coin-operated machines as a general. Now, how to identify the fine-grained classes of the coin-operated machine? First, we will see how to identify the drink vending machine. We have observed that all drink vending machines emit a unique and loud sound when the drink is pulled down from the machine into its outlet. The sound the sound the sound will be like that. Our Fourier transform analysis of this sound, we see that this sound forms a clear peak on the frequency spectrum at a certain frequency band. So we will leverage this peak in order to identify the drink vending machine. At the real time, we will check the audio signal strength on this frequency domain, and if there is a significant change that increase a significant change in the amplitude of the signal that exceed a certain threshold, we will confirm the detection of a drink vending machine. On the other hand, if you saw this figure, which shows the Fourier transform of the background noise, we will see no peaks at this frequency. Now, to detect the ticket vending machine, we have also observed that all ticket vending machines in the station emit a unique beep sound several times during user interaction. This sound will be like that. So, also, when analyzing the Fourier transform of this sound, we observed that it forms a clear peak at another frequency spectrum, at another frequency band in the frequency domain, where there is no peak on the background noise. So also we will leverage this peak in order to identify the ticket vending machines by using similar methods. We will skip how to identify the coin-operated locker because it will be, you can see the details on the paper. Now to identify the restroom, we when entering the restroom area. Second, during the usage of restroom, the user has to be stationary for some time. However, these two features are not sufficient to identify the restroom. So we will use active probing, which means that we actively probe the environment by emitting a sine wave at certain frequency band and analyze the impulse response of this sine wave. The intuition is the acoustic characteristic of any environment depends on its ability to absorb sound. And since all public restrooms have common infrastructure like floor and walls that are water resistant and sinks, we find that they have a unique sound absorption coefficient. So we will use this fact in order to identify restrooms. So after emitting this sound wave, we will locate it on the audio signal, and we will extract several features from it, like MFCC and other features, and forward this to a trend classifier, which will identify whether there is a restroom or not, as shown on this figure, which shows the impulse response of in restroom and the impulse of response in other areas. Now, to identify other features like platform-related semantics, which includes the platform itself, how to identify the platform itself and its tracks and waiting line. Waiting line is the most important because it will give us insight about the location of train cars when the train arrives, which is good in order to navigate user to their cars if they have reserved seats. This video shows a typical user behavior on the station. So the user walk on the station and join a line and then step aside to free space for alighting passengers. And when alighting passengers will go away, as we will see now on the figure, when all alighting passengers go away, the user will walk into the train and then change his direction to be aligned over the train and then wait for a while the train to move and the train will move. This sequence of micro activities are reflected to unique sensor signatures. So, for example, the user starts by walking for a while on the platform, which is reflected to high acceleration variance. And second, the user joins a line, which will reflect it because when the user joins the line, he will be stationary. And at the same time, before joining the line, he has to change his direction. So there will be a low acceleration variance because he is stationary. And at the same time, he will change his heading. So there is a surge in gyroscope reading. After the user joins a line, he will step aside in order to free space for alighting passengers. When he steps aside, he walks slowly and with slight change in his direction because he will walk with a certain angle. After the alighting passengers move away, he will wait for a while. After step aside, he will wait for a while for alighting passengers to move away, which is reflected to low acceleration variance. Then the user, after all alighting passengers have went away, he will walk into the train, which is reflected by high acceleration variance because he is walking. And at the same time, if we see the gyro reading at this section, we will find that there is a change because the user has to change his direction to be aligned with the train. And after that, the user have to wait for the train to move, so the user will be stationary. And after that, when the train started to move, we will see a unique signature of acceleration, which can be detected by any transportation mode detection. And we also add another feature because when the train started to move, there will be a significant magnetic distortion from the train machinery that will be sensed by the magnetic field. Finally, when the train stops at the next station, there will be a low acceleration variance, and the user walks away. We will leverage this set of micro activities to identify all the activities on the platform and on the train, which will give us insight about the platform area and the location of waiting lines and the platform track. Now, to identify the fare collection gate. As we know, the user can cross the gate by using a ticket or an IC card. In both cases, the user behavior consists of a temporal consequence of micro activities. First, the user walks normally to the ticket, to the fare collection gate. Second, when the user approaches the gate, the user has to slow his walking speed, which is reflected to a negative slope of acceleration variance, as shown here. The user starts to slow. In both cases, the user starts to slow his walking speed because he is approaching the gate. accelerate his movement. And at the same time, as shown here and here, there will be a magnetic distortion resulted from the metals and electronic chips installed in this gate. However, the difference between you crossing the gate using a ticket or crossing the gate using IC card, when the user crossing the gate using a ticket, he has to stop for a while, which is reflected to acceleration variance that reach for a while to zero, which means that the user paused for a while in order to put the ticket into the vending machine. However, using IC card, the user have not to stop, he just slow, but the acceleration variance will never reach to zero because the card reader can recognize the IC card without forcing the user to wait. Finally, the user walks away, which is reflected to high acceleration variance. Now, we will move to another type of semantic, which is elevation change semantic. We will see how to identify an elevator. The elevator also consists of a temporal consequence of microactivities. The user first waits for elevator, which is translated to low acceleration variance, and at the same time, when the elevator arrives, the user walks to the elevator, which is translated to high acceleration variance. And when the user enters the elevator, the user changes direction in order to face the elevator exit door, so there will be a surge in the gyroscope reading. After that, the user waits the elevator to move, so there is a low acceleration variance. And when the elevator starts to move, there will be a unique signature on the accelerometer reading, which is start by acceleration, because the acceleration will go high when they start to move, and then static acceleration because the elevator doesn't change its speed, and then the acceleration when it starts to stop. We will use also the sequence of these microactivities to identify elevator. Now, after the elevator is separated, the remaining traces of elevation and change semantic can be classified as escalators or staircase. So we will check first whether the user has low acceleration variance, because if there is low acceleration variance, it means that the user is stationary. And if the user is stationary, it means that the user is using escalator. Because if the user is using escalator and he is standing on the escalator, so the acceleration variance as shown on the green curve is very small because the user is stationary. While if the user is climbing stairs, the acceleration variance will be very high because the user is moving vertically. So after separating standing on escalators, the remaining traces will be climbing either staircase or escalator. We will first separate a special type of escalators or stairs called have-landing stairs, which have a landing on their middle. This have-landing stairs force the user to change his direction completely on the middle of the elevation and change period, which is reflected to a surge of gyroscope reading. After separating these traces, the remaining traces are either climbing staircase or escalator. So we will depend on the magnetic distortion, because if the user is using escalator, there will be a magnetic distortion from the escalator machinery. If there is a magnetic distortion, means that the user is climbing escalator. Otherwise, the user is on a stair. Now to evaluate our system, because we don't have much time, we collected data by 16 users in 8 different stations in Japan that run by different train companies and using different Android phones, and passengers or users hold the phone in different placement in their hands or pockets. And we collected 2 different datasets: scenario-based dataset, which is a controlled experiment where the user moves in pre-specified trajectories, and a free dataset, which is collected by passengers during their daily commutation. Here we report the accuracy of the semantic detection of the system as shown in the 2 table, which shows the false positive and the false negative detection of the semantics. On average, the accuracy of semantic detection is good. However, there are some semantics that are colored in yellow, which have a not good but fair accuracy. We report on the paper how this semantics, why this semantic is tricky. Now, we report the semantic location accuracy as shown on the figure. The semantic location accuracy depends on the number of the samples of each semantic. When the number of semantics increase, when the number of the samples increase, the location error decrease. However, we can have an average location accuracy of all semantic of about 2.5 meters using 40 samples. This because we have high semantic density in the stations, and we use offline applying localization. Finally, to generalize our work, we do two different experiments. We compare the performance of our system that, just to conclude our work, we provided an automatic construction of semantic on-door floor plan for railway stations that can provide an accuracy of 2.5 meters by using 40 samples, which avoids the intensive work used in manual floor plan construction operation. For future work, we should handle dynamic change, which means that some semantics are moved or removed or added by period clustering. And we can apply our system to other indoor environments like airports, which have similar semantics. However, our major problem is that all experiments are done only in Japan, which have consistent